Welcome, everyone. It is a pleasure for me to introduce Edgar Dobriban. He's an assistant professor at the Wharton School in the Department of Statistics, and he has been an assistant professor since 2017 when he graduated with a PhD in statistics from Stanford. He has won many numerous awards, and the latest one is a career award from NSF. So congratulations, and he's going to talk about asymptotic perspectives on sketching.
Yeah, so thank you, Soledad, for the kind introduction. And so first, I'd like to thank the organizers for putting together this really wonderful seminar series. And I myself have attended a number of talks before, all really great speakers, and watched some recordings on YouTube as well. So it's all really terrific service to the community, and it's very valuable in my view. And thanks so that specifically for the invitation. So as I mentioned, I'm going to talk about asymptotic perspectives on sketching, and this is work over a few years with a number of different collaborators. So I'll highlight here Sifan Liu, and Jonathan Lacotte, who are PhD students at Stanford, Mert Pilanci, who is a faculty member at Stanford, David Woodruff, faculty member at Carnegie Mellon, and Fan Yang, postdoc at Penn. So okay, so I have a few big picture slides that I guess we all know about this, and so I'll just kind of flash through them quickly. So we all know that we live in the age of data. Lots and lots of digital data is recorded and generated and recorded every day from the web. We have all kinds of web pages and links and ads and reviews. In science, it's closer to home. We have things like genetics data and health records and high energy physics, and it's a real challenge how to efficiently analyze them and extract the valuable information from them. So the problem is that pace of computing has not necessarily kept up with the pace of our ability to record the data. So we just have these huge data sets, and sometimes even storing them or loading them into memory or doing basic computations or communicating them to other places is a challenge. So I see. Okay, yes, please ask. Feel free to ask questions even during the talk, especially if something is unclear. I'd love to just clarify and make sure that you get something valuable out of this talk. So in the end, a lot of this ends up being trying to, for me, it ends up trying to think about and develop fast algorithms and understand how they work. And in the end, they end up saving some real resources. At least that's what I think, that if there's a fast algorithm, then we have to wait less time for it to finish, so we can do more things with our own time. And there's lots and lots of different approaches. We all know from computer science, statistics, optimization, all these different fields come together and produce a variety of ideas and tools. We all know about efficient data structures. We are taught in college, and online algorithms and so on. And today I'll focus on a particular class of algorithms, randomized algorithms. Let's see here. So to be a little bit more precise, there's a lot of data processing problems that can be modeled via mathematical object matrices. So if we do something like we collect some data on n individuals, maybe some patients in a clinical trial or something like that, and we measure their features like the demographic characteristics, their lifestyle features, preferences, genetics, results of medical tests and outcomes, then a way to represent this data in a form that's kind of convenient to process is that we can take these measurements, its features, and then we put them into a vector in some particular order, and then we put those vectors as the rows of a matrix. So we don't suddenly have this n by p data matrix where n is the number of data points and p is the number of features or observations. So features, yes. And so if we have a lot of data, then we suddenly are faced with this, we can think about this as having this huge matrix. So we want to process it in an efficient way. Suddenly we, we can think about mathematical operations such as matrix multiplication to reduce it into a smaller matrix and still keep the structure of the original data. So for instance, if you're interested in reducing the sample size because we have a really, huge sample, then we can think about taking some sort of matrix, which I'll talk about a lot later in the talk, an R by N matrix, R is less than N, and then instead of working with X, suppose that I can somehow compute this matrix product S times X efficiently. Now suddenly I have a much smaller matrix, and I can somehow hope that some part of the structure of X will be preserved by this matrix product. Of course, it's a question of what can I do with this. That's a lot of what this talk will be about. But you can imagine that I have a big matrix, I multiply it with another matrix, I get a small matrix, and that's one of the most basic kind of primitives in randomized algorithms. Similarly, for a dimension, I can multiply on the other side. So now, how do we choose these matrices? One very natural idea is to randomize, kind of choose some sort of random structure on S or T, and then this leads to random projections, even if it's called random projections in the literature. Sometimes even if the matrix S is not strictly a projection, for instance, it can have IID Gaussian entries, so may not be strictly a projection matrix, but still it's kind of a randomized matrix multiplication. Okay, so and this kind of basic primitive has found a lot of uses in various areas of, broadly speaking, data science. In theoretical computer science, there's a nice book by Vempala that describes a variety of problems that this can solve. In randomized numerical linear algebra, there are several works. For instance, approximating matrix multiplication, approximating SVD. In various statistics problems, such as nonparametric regression, ridge regression, two-sample testing, classification, some clustering problems and PCA, various optimization problems, convex optimization, and also in econometrics. So in some applied areas, including in econometrics and genomics, there are researchers who have explored the use of these type of randomized projections in their own work, in their own communities. So these are people who are, scientists, not mathematicians, and they want to solve their own problems. And so they still use, they're interested to use these random projections. So this is kind of a broader impact of the random projections in some sense. So let me talk about this genomic example just a little bit. So this is a work by Galinsky and collaborators, and Nick Patterson, Alex Price are kind of well-known names in population genetics. So it was a few years ago. They are interested in analyzing some large, basically data set on genetic variation, where you kind of count the number of copies of genetic variants across the genome, and you may have, even after reducing the data significantly, something like 160,000 genetic variants, and you have something like 50,000 individuals. So it's pretty large. Certainly you need to think before analyzing it. Okay, maybe it's even possible to analyze on a computer without any approximation. Maybe it's feasible, but you need to think. If you just try to run a matrix multiplication, NP its complexity might be np squared or pn squared, something like that. It's going to be very expensive. So they developed and built on some of the fundamental randomized algorithms that other people have developed earlier, and this is something that they were interested in for their own scientific analysis. Here's just a random kind of picture from their paper. They show that using this so-called fast PCA method that they developed, the first two principal components can be used to sort of separate, cluster the individuals in the data set. So you can see here the samples from Italy and I guess Scotland, Ireland, and Czech Republic, Poland, Russia, and so on. So while being very vague, the point that I'm trying to make here is that kind of real scientists are interested in analyzing massive data, and they're already exploring these uses of randomized projections. So I'm going to talk about mathematical aspects of the problem, but we should know that there are real real scientific applications. Okay, so myself, I'm interested in the mathematical foundations, and I'll talk about some works on developing a kind of asymptotic perspective to study randomized projections. I should say that another kind of synonym of randomized projection is randomized sketching, or sometimes just sketching. So I'll just be using these kind of exchangeably. So, and I think that this perspective leads to some nice mathematical results. I'll try to show you some of them, and yeah, we can discuss how nice they are. So let's see. So we have a few works. We started from linear regression, studied ridge regression, some sort of iterative methods for linear and ridge regression, PCA, and matrix inversion. And these were published in various machine learning conferences and also in IEEE transaction on information theory in kind of the past few years. And today I'll actually mostly focus on linear regression. I have a few slides at the end about these other topics, but I'll just mostly focus on this because this is somehow the most fundamental one, and it's pedagogically, it's certainly the one that I think should be presented first. Okay, so now to be more precise, let's start with the more formal presentation. So here, linear regression is a basic problem where we want to study the dependence of an outcome of interest on some predictor variables. So we want to study the dependence of heart, blood pressure, heart rate, something like that, a continuous outcome, on features like genetic composition or lifestyle choices or whatever. And if you are in statistics or you have some statistical background, you will most likely, I will most likely not have to convince you that this is the single most important kind of core problem in statistics. And there are lots of other things, but a lot of other problems are basically about how to reduce that complicated problem into a type of linear regression. So it's really kind of a central thing. And okay, so here, so what we will have n data points, and as before, they will have the features arranged into an n by p data matrix X. And in this talk, I'll assume that n is larger than p, but p can be still quite large. Of course, this was not the case, for instance, in the genetics example, but we have in our follow-up work in ridge regression, we actually have also p larger than n, so we can handle that as well. But this is just simpler to present. So then the outcomes yi, these are, let's say, the blood pressure, they will be arranged into this n by 1 vector y. So this is just the arranging the data. And now the actual linear model, statistics 101, is that we take y and we assume that the columns, that y is actually a linear combination of the columns of x with some unknown regression coefficients beta and plus some noise. So, so of course we don't know beta and we don't know epsilon, but we assume that beta is fixed and epsilon is random. So random noise, the random noise entries are uncorrelated in this talk. So we assume that the mean of epsilon I is 0, and the variance of every epsilon I is equal to sigma squared. So this is the standard linear regression model, and the most basic estimator, again, something that is the kind of core upon which a lot of other estimators are built, is the ordinary least squares estimator. So it just has this very simple form, x transpose y, x transpose x inverse. So it also comes from solving the minimizing over all beta tildes the L2 norm of y minus x beta tilde. So that's another way to, that's where the least squares come from. Okay, so so we, of course, the complexity of full least squares is np squared if we do it naively. And we are thinking about a setting where n and p are large, so this is too expensive. And here is now the kind of basic algorithm, basic randomized algorithm. What we are going to do is we're going to generate some sort of random matrix. Which type I'll talk about in a second. Some sort of random matrix S. We are going to compute the matrix product here, Sx, Sy. Maybe there are other ways to implement this, but just conceptually we compute the matrix product and matrix vector product, and then we do least squares regression of this vector on this vector. So let's just call it x tilde y tilde. So we will have beta hat S for beta hat sketched is the least squares of y tilde on x tilde. So we take original data, we project it all down to a hopefully smaller sample, smaller number of samples, and then we do regression on that. Okay, so this, what we hope is that if we use S here, which is, has a small r, then we save some computational efficiency. And hopefully we don't lose too much in terms of the statistical efficiency, meaning that the error that this randomization introduces is not too large. That's all that this talk is about, to try to understand what is the trade-off and how much do we actually basically lose for a certain dimension. Okay, yeah, so this is exactly what I said. Hopefully this is faster and it will be less accurate, but by how much and how many dimensions do we need? And then of course, how should we choose the sketching matrix? Should we do just a simple uniform sampling of the rows of X? This is sometimes what's called subsampling in statistics, and it has there are beautiful books written about just subsampling. Should we choose the matrix S to have something like IID entries, like ternary entries or Gaussian entries, or should it be HAR, uniform over orthogonal matrices, or these more fancy randomized Fourier transform or leverage sampling? Or what should it be, and what are the considerations? And turns out that every one of these works under slightly different conditions on the data matrix X. So if we have more structure on the data, we kind of want to adapt the choice of the sketching matrix to it, because it will lead to a better behavior. Okay, so in the next few slides, I will go through some of these I will go through these in more detail. And then finally, hopefully as a kind of culmination, I will present some results that hopefully answer some of these questions. So first question is, how do we measure the statistical efficiency? So what is the kind of metric that we are interested in? So of course, there are many standard measures for evaluating an estimator beta hat of a parameter beta. For instance, the mean squared error is just the average of the L2 squared L2 norm of the difference between beta hat and beta, and the average is over the randomness in beta hat. And So it turns out in our setting where we look at the problem, there's a lot of concentration of measures, so you don't need to average over the random sketching matrices. So that could be a subtlety, but it's just concentrate, so you don't need to worry about it. It's just the average over the random noise in the outcome y. Of course, because we are in a regression context, we can also look at the residual error. So this is we just look at y minus x beta hat, which is the residual, and we again look at the average L2 norm of this. Again, if we're in a regression context, we can look at the test error. Let's say xt yt is a test data point drawn from the same distribution from which the training data points are drawn. And let's say that we use a linear predictor, xt transpose beta hat. So we have beta hat and we just observe xt, predict yt hat with this. So then if we use this to predict yt, then we can just look at average value of yt minus yt hat squared, or just average value yt minus xt beta hat squared. So we can look at all of these measures, and actually in our work, we basically evaluate and quantify the performance in each of these metrics. And so then the next question is, I want to compare estimators, or basically algorithms. I want to compare these statistical algorithms. So how to compare them? There is a standard notion called the relative efficiency, which is very intuitive. It's just the ratio of the errors. So I have here two estimators. Beta hat is the least squares estimator, and beta hat s is the sketched estimator. So I can just look at this. This is not standard. The variance efficiency, the name is not standard. The name relative efficiency is standard, but variance efficiency just is just me calling it in our papers. So this is the ratio of the mean square error of the sketched estimator compared to the mean square error of the full least squares estimator. So of course we expect this one to be less accurate. So we expect this to be larger than this, and we expect basically VE to be greater than or equal to 1, or unity. So we want it to be as close as possible to 1. The smaller it is, the better. Same thing we can do for residual efficiency. Just take the ratio of the two residual mean squared errors. And for the out of sample efficiency, we can take the ratio of the expected test errors. Okay. And then, so that is basically all we need for in terms of like how we compare the estimators and what are the metrics. But then what matrices are we going to look at? So roughly speaking, in this literature, there's kind of 3 broad classes of sketching matrices. There are sampling type methods, which sample, unsurprisingly, the rows of X in some independent form, either just IID, so treating the rows identically, or according to some form of importance. And I'll talk about what the importance means in the next slide. I'll define this in more details. There's also sketching matrices or projection matrices where the entries of this S are drawn IID from some distribution, like IID Gaussian or IID like the plus minus 1, plus minus 1, 0, or something like that. And then there is the most complicated but probably most interesting one, which are the structured orthogonal matrices. And here we can take this matrix S to be some sort of randomly chosen rows from a structured orthonormal or unitary matrix, such as a Fourier transform or a Hadamard transform. And I have some kind of quick, so first there's a few things here in this slide. There's a kind of heat map of some of these. So there's a heat map of a Gaussian sketch. You can see it's kind of very random looking. It's and it's continuous valued entries. It has continuous valued entries, so it's an example of this. There's also the plus minus 1 random sign sketch. It's also an example of this, but it's binary, so maybe it's faster to multiply depending on hardware implementation. There's also the randomized orthogonal sketch. So this is an example of the structured orthogonal. I will explain how it arises, but you can see there's much more structure in here. And then I guess I didn't talk much about these sparse sketches. Maybe that could be like a fourth category here. And we don't have a lot of results on that, so I didn't emphasize it. But let me go and explain every one of them in a little bit more detail. So uniform sampling. So among sampling methods, uniform sampling is the simplest one. And here S is a matrix that just takes every row of X with equal probability. Very simple. With the same given fixed probability. Leverage score sampling, you take every row of X with a probability that's proportional to the leverage score that's defined here, HII, Xi transpose, X transpose, X inverse, Xi. And so you may recognize this matrix H as the hat matrix. At least in statistics, it's kind of a standard thing. And these are just the diagonals of the hat matrix. And here's a picture from a nice review where you just see a two-dimensional data plotted, and these are kind of color-coded somehow proportionally to their leverage score. So these are the points with the high leverage score, low leverage score. And you can imagine that if you want to fit a line somehow through a third dimension here, somehow, maybe that's a third dimension that you want to fit, then these are the points that are most influential. So if you want to sample, you want to be efficient and sample only a few points, you should prioritize these ones. Okay, so the key problem here, though, is that computing these leverage scores exactly is basically as difficult, at least in a naive implementation, as solving the regression problem. Exactly.
There's a question. Sorry for interrupting.
Yeah.
So do you take into consideration the responses as well when you consider the scores?
So this is a standard procedure, and this does not take into account the y. But actually, so that making a good point. So a very good point. For instance, if the y is varying somehow in a direction that's orthogonal to this, I don't know, maybe source of large direction of variation, then one should somehow reduce or sample somehow according to that in some way. This is only looking at the structure of the X, irrespective of the Y. So that's the.
Would it make sense to look at the joint distribution and do like the scores in that space? I don't know. I don't know. I have no idea. I'm asking.
No. Yeah, certainly, maybe. Yeah, maybe. And I think some of these works, that look at principal component regression, or I think your work as well, that kind of tries to look at these adaptive sort of reduction methods. I think that is, yeah, it's going in that direction. This is trying to, okay, so I should say that the methods here are what is called data oblivious, or oblivious, kind of relatively oblivious sketching methods. So they are, you see, for instance, uniform sampling is just completely blind to whatever structure is in the data. So it can be fast because of that, but it can be maybe not the most efficient. Yeah, so that's, I mean, those are the interesting questions. Yeah. Yeah. So yeah. And so somehow one of the main problems here is that computing these leverage scores exactly, is as difficult as solving the original problem. So in fact, one can try to estimate them by something called Hadamard transform. I'll introduce in the next slide. But in fact, one could use the Hadamard transform directly. So that's probably people are still debating about that. Okay, so the easiest type of sketch to understand is the one with IID entries. Let's say S has IID standard normal entries. Very easy to, understand and code. Sparse projection, IID entries plus minus 1 with probability 1 over 2s, 0, 1 over 1 minus s. Sij could be general, mean zero variance 1 random variables. The problem with this, again, is that computing S times X can take a very large cost. So it's hard, it's almost never, you almost never actually gain anything computationally here. So it's a nice theoretical construct. But if I take R to be large, I'm not gonna save anything. But you might save something if you use one of these structured orthogonal sketches. So first of all, unstructured sketch, an unstructured hard sketch, is uniform over the set of partial orthogonal matrices of the appropriate dimension that you want. But that's also hard to generate and multiply because it's a dense matrix and there has no structure. So there's no way to generically speed up. The cost is as high as matrix multiplication. But if you do a Fourier transform, then suddenly you can get some speed up. So you can think about, let's start with the discrete Fourier transform matrix F. Just, reminder, the entries are 1 over square root of n, and then you may, you compute the appropriate powers of the roots of unity. And then there's a little bit of extra work to be done, but very little. So I take this matrix F and I multiply it by Q. Q flips the signs of the rows of F, and this introduces some additional kind of randomness that helps avoid some kind of corner cases where all the data is positive and the Fourier transform, one row, for instance, is all ones. So it may have some kind of odd behavior. But P can be a uniform permutation matrix. So again, this is to avoid some corner cases. And then finally, D is just the matrix that randomly selects the rows from this FQP matrix. So once you have that, then you can let your sketching matrix be this this matrix. And similar thing that sometimes is kind of emphasized in this literature is the subsampled randomized Hadamard transform SRHT, which has a kind of conveniently expressed recursion starting from age 1 equals 1, and then for powers of 2 you just use this recursion. And then if I have a value that's n between powers of 2, then I look at a matrix that's larger than that and I select the rows and columns randomly from the larger Hadamard matrix. But in fact, the Hadamard matrix itself is actually just a Fourier matrix, the Fourier transform for the power of 2. So in both cases, I can still compute the matrix product via the fast Fourier transform more efficiently. So this actually gains in computation. Okay, so that's actually, there's a lot of, you see that there was no results here. I haven't given you any results, but there are suddenly, in one slide, I can give you all the results. So this was all just introduction, and in some sense, these are all of our results. So let me just explain what's going on here. So this table, remember that we're trying to do sketching in linear regression. Okay, we have a linear model which has an n by p matrix, n samples and p features, or n or p dimensions, n is larger than p, and then we sketch into a r-dimensional sample dimension. So we have n greater than r greater than p, so r is between these two. And then remember that we looked at variance efficiency, right? The average value of the ratio of mean squared errors, the ratio of the average value of mean squared errors. and the out-of-sample efficiency, the ratio of the prediction errors, for a number of different sketching matrices. So how do you read this table? So for S that has IID entries, let's say IID Gaussian or IID plus minus 1 zeros, and X that is effectively completely arbitrary, the variance efficiency can be read off here approximately for given NP and R, and it is approximately equal to 1 plus n minus p divided by R minus p. So basically, this table is kind of a dictionary or encyclopedia, of results about all the possible efficiencies. And I haven't listed here the third efficiency, the residual efficiency, but we also have results for that. It just didn't fit on the slide. So okay, what's interesting here though, because there's like a lot of formulas. What's interesting? So what is interesting is that for Haar or Hadamard matrices, so these are the orthogonal matrices, if you look here at the variance efficiency, it's just n minus p or minus p. So it's strictly less. It's somehow by a, I think it's just by a kind of coincidence. But it's strictly less by 1 than the variance efficiency for the matrices with IID entries. So remember that variance efficiency should be small. If it's small, that's good because we're doing close to the gold standard of least squares. So this is saying that the orthogonal matrices are uniformly better than matrices with IID entries. So, most of the literature focuses on these matrices with IID entries, IID Gaussian and so on. That's all that the TCS, theoretical computer science literature, focuses on. Because it's so easy to analyze. I can take an off-the-shelf matrix concentration inequality, maybe not so easy, but I can, there's lots of concentration inequalities that I can take and I can analyze and I get results. But empirically, the orthogonal matrices work better, and I'll try to explain why, somehow because they preserve the geometry better. And here these results actually show that. So the results support the fact that the orthogonal matrices work better. So this is in some sense the most interesting comparison in this table. We have results for OE and for leverage score sampling under some other model. We have some results that I'm not going to detail. Let me look at this question here. Does ortho-invariant mean that the leverage scores are all equal? So yes, what is this assumption on X that is ortho-invariant? So formally, it means that the distribution of X is the same as when I rotate it arbitrarily from the left by an arbitrary rotation matrix. And in fact, it will kind of mean that the leverage scores are, roughly speaking, concentrated or around the same value. So that's why uniform sampling works. In an elliptical model, here you can have, I'm not going to talk about what this is, but basically you take something with an IID entries, and then you multiply it with the covariance matrix and multiply it with some diagonal here. Then the leverage scores can be all over the place. So then uniform sampling doesn't work as nicely, and it basically becomes more complicated. Okay. All right. So that's the result. And a few comments that somehow what is interesting is that there's no hidden constants. These are the actual high probability sort of approximations. I'll make it more precise, asymptotically exact results. But you can use them as sample size calculations if you have some kind of statistical training. You know that you can plan ahead your data analysis. How many dimensions do you need? For instance, let's say here, how large of an R do I need to make this quantity at most 1.25? If I don't want the variance efficiency to be too larger than 1.25, then I need an R to be, and I can calculate. I can just solve this equation. This quantity is equal to 1.25. Solve for R, N and P I know. I have my data, so I can find the answer. Show separation between the sketching methods. And I already mentioned this Hadamard was better in practice, but there was no proof. Okay, so let me show you a few numerical experiments to try to illustrate that these are accurate. So let me take n equals 2000 data points, 100 dimension, and the r, the dimension, the number of samples into which I project down, ranging from 300 to up to 2000. Of course, I should never make it more than 2000. And so we generated a data matrix X randomly and then fixed it in this experiment. We looked at standard Gaussian distribution and multivariate distribution with some sort of autoregressive covariance matrix. Notice here that the assumptions on X, so this first one satisfies all the assumptions. It satisfies the uniform level score ortho invariance assumption. This one may not have uniform level scores. And then we generate beta epsilon as Gaussian, and then generate a bunch of sketching matrices and compute the least square estimator and the scared least square estimator, and just empirically find the variance efficiency. Let me see a question. In what application do we see orthogonally invariant or elliptical X matrices? Yeah, so from my perspective, actually, one of the kind of outcomes of this theoretical analysis is that it's not often that you know for sure in an application that you would see uniform, you would see one of these two. But these conditions are essentially required to get such a behavior. And we'll see that when such a behavior doesn't happen, then these kind of good results don't hold empirically anymore. So actually that suggests that this essentially these matrices, and specifically the Hadamard or Fourier matrix, comes out on top as the most preferred matrix because it works under much weaker condition. It's fast and it has good statistical accuracy. So uniform sampling works as good as Har or Hadamard under ortho invariant X. So if the data is really has some this sort of uniformity behavior, then the problem is completely straightforward. I just do a uniform subsample. But in practice, it's like rare, and I wouldn't bet on it, or I wouldn't trust that it holds in practice. Okay, so here's the simulation. And here's the result. So what are we seeing here? So here on the x-axis, we show R by n. So this is the ratio of how many samples effectively do I lose. So 0.5 means that originally I had 2,000 samples and I have 1,000. And I show the variance efficiency. So there's the curves. Pink one is the 1 plus n minus p. So this is the non-orthogonal sketches. And the gray one is the orthogonal sketches. So you see here the pink curve here, the non-orthogonal sketches, and the orthogonal sketches here below. And in this example, and actually much more generally, what you see is that the simulation results align really well with the empirical results. So our predictions are accurate. And this is what I mean that they're accurate. So if I predict, if I predict that the variance efficiency is 6, it's going to be 6 plus minus 0.1. And okay, we looked at the AR covariance, autoregressive covariance matrix, and then you see similar things, except you see some much higher fluctuations, for instance, for the Har matrix. So that's one problem with the Har matrix, that it's discrete. And so with a small probability, which just happened to happen here, it can become close to singular. So if the matrix is close to singular, it will just, after projection, you may just have a really bad condition number, and just, the problem just explodes basically. And kind of maybe for the Gaussian, Gaussian matrices are, well, in this case, it turns out maybe not due to this discreteness, but due to the structure of the data itself, which is not so uniform, you can see some peaks. But in general, even for a very difficult, I want to say that this is a very difficult sort of data structure model, our results are still okay. Can the fact that we have b equals 2 for r equals n be explained other than from the theoretical results? So that's actually a very good question. Here, if I have r equals n, so I project into the same dimensional space, I don't reduce the samples, the number of samples, I get a variance efficiency of 2. Here I get a variance efficiency of 1. So that's this one makes sense because I'm just rotating the data orthogonally, right? Here, the reason why I get this is, so I don't know a simpler explanation other than, you know, this actually corresponds to basically a rotation and then scaling by the eigenvalues of effectively the Marchenko-Pastur law of appropriate, you know, of aspect ratio equal to 1, and then somehow after that rescaling, there's a heteroscedastic problem, and that's what comes out of the calculation. So in short, you know, I wish I had a kind of more snappier answer, but yeah, I don't know. Somehow there's only a rotation. So here, these matrices, they rotate and they also distort the geometry somehow, the space, because they scale by the eigenvalues of the kind of Marchenko-Pastur distribution, which, if you don't know what it is, I'll explain in a second. Let me see another question here. Do I make any assumption on the distribution of the noise in the theoretical results? No, because here I only look at the mean squared error, and the mean squared error only depends on the first 2 moments of the noise. So I assume that the noise has mean 0, variance sigma squared, and they're uncorrelated. If I wanted to do something more complicated, some higher order, you know, high probability or something like that behaviors, then I would need to make more assumptions. Okay. Okay. So maybe I would like to. So Matthew, how many minutes does the talk normally go until? How much?
Yeah, it can go for 50 to 60 minutes. If you want to talk a bit more for 5 to 10 more minutes, that's fine.
Okay. So so maybe I'll skip this empirical data analysis. We have a very nice empirical data analysis where the predictions align well with the theory. You can easily read this on your own. But I would like to talk a little bit more about the mathematical aspect. So the proofs rely on asymptotic random matrix theory and free probability theory, which is somehow a perfect fit for these areas because the algorithm itself that we're analyzing is random. So we need very weak assumptions. And the standard kind of textbook things like the Marchenko-Pastur law are not enough in the for all of the results. But what we found out is that there's some recent results, very nice results by Greg Anderson and Brendan Farrell, that on asymptotically liberating sequences in free probability, that we were able to basically leverage and kind of make the connection between the and use. So this is the paper from 2014, and let me give you kind of a flavor of how the arguments go. So we want to characterize the mean squared error of the sketched estimator. So we can write this out step by step, and we see that it equals the average value of the trace of QQ transpose, or the Frobenius norm of Q squared, where Q is equal to this matrix. So you can just, you know, this is like a homework exercise. You can check. And the Q is this X transpose, S transpose X inverse, you know, kind of looking matrix. So for different, and now what we have here is we want to compute, sorry, there's an expectation here missing. the average value of the Frobenius norm of Q, which also, you see that it depends on the singular values of Q, where Q has this kind of relatively complicated, if Q has this structure. So depending on what we assume on the random S or random X, we can do some calculations. So for a Gaussian S, if we assume that S is Gaussian, then we can use the properties of the Wishart matrices, which are, from the 1930s onward, kind of being developed. So these are very, well known in multivariate statistics. For S that has IID entries, we can use a Lindeberg swapping technique. That specifically we use the results from Shurev Chatterjee's nice paper. And for more complicated S, though, for S matrices that have orthogonal entries, for S matrices that were orthogonal, we needed to do something a little more. But at least we got a simplification that this inner term disappears when you look at QQ transpose, so it just reduces to the trace of this inverse X transpose S transpose S X inverse. So here's the kind of most, here's how we make the connection to free probability. So remember that X was our data matrix, can be arbitrary, and S has the forms D, H, Q, P. D is this subsampling matrix that chooses the rows. So we take it as diagonal matrix with diagonal entries that are Bernoulli R by N. This one is a matrix of 0, 1s, so it selects random rows. H is this Hadamard matrix that I mentioned to you. Q has plus minus 1 IID diagonals, and P is the uniform permutation matrix. So when I look at this X transpose SX, I can write out explicitly, just plug in this DHQP. And there is one step here that in the middle, because I have a diagonal matrix, I can basically put in an extra Q and the P without any, without changing the value, and see that it has the same distribution as X transpose W dWx. Maybe it might not be it might not be possible to kind of follow this. I apologize, but you can check this later on your own if you're interested. That basically, if I look at this signed Hadamard matrix, which only consists of a random permutation, a random sign, and the Hadamard, then this matrix that I'm interested in, it has the same distribution as X transpose this complicated looking matrix in the middle and X again. And so the key thing here is that Anderson and Farrell have showed that the two matrices here that I have, so W here is in the middle, and then D is in the middle, and this WX X transpose W, they are asymptotically free independent. And turns out what that means for us, due to lack of time, well, what I'll just say is what that means for us is that asymptotically their traces decouple. So the average value of the trace of AB will be well approximated by the average value of trace of A times average value of trace of B, where A and B are these two matrices. Free probability is a little more complicated, and it allows kind of arbitrary product of polynomials of matrices to be kind of decoupled in appropriate ways. But for us, we only need a very simple kind of, we need a simple version of that. So let's see. So that's all for the mathematical. There's much more kind of technical steps to do, but that's the basic idea. And I want to also emphasize there's nice work, related work from Raskuti and Mahoney that also looked at effectively the same problem, and they showed upper bounds on the prediction efficiency and residual efficiency. I guess I call this OE and RE. The point is that if you do a simulation, you will see that our results align perfectly, whereas their results are kind of a relatively larger upper bound. So somehow we get the exact value asymptotically and also very high, very accurate in finite samples. Okay, so that's actually all. And yeah, so please let me know if there's any questions. Thank you very much.
All right, thank you so much. Excellent talk.